In the first lesson, we have defined what a digital system is. In this second lesson, we are going to present several methods of specification of a digital system. The specification of the working of a digital system can be done in a functional way, describing the relation between inputs and outputs, but without information about the internal structure. Furthermore, we will make a distinction between explicit functional description and implicit functional description based on an algorithmic description. Let us start with an example of explicit functional description. For that, consider again the boiler controller with two modifications. The desired temperature, that is the value of the pause signal, is assumed to be a constant equal to 20 Celsius degrees, and the measured temperature has been discretized so that the temp input signal values belong to this set from 0 to 50. Then, with those modifications, the working of the controller can be described in a completely explicit way by a table that for each value of the temp input signal gives the value of the on-off output signal. If temp is between 0 and 19, then on-off is equal to on. If temp is between 21 and 50, on-off is equal to off. And if temp is equal to 20, then the state of the boiler, running or not running, doesn't change. Now, the same specification could be expressed by a very simple piece of program. If temp is less than 20, then on-off is equal to on. Else, if temp is greater than 20, then on-off is equal to off. It's a program equivalent to the previous table, and this is an example of implicit functional description by means of an algorithm. Let us see a second example. A system that adds two two-digit numbers. X and Y are two-digit numbers so that they belong to the set 0, 1, 2, and so on up to 99, and the other computes the sum z equal to x plus y, so that the output z belongs to the set 0, 1, 2, and so on up to 198, and the result is a three-digit number. The simple, the classical pencil and paper algorithms works as follows. Consider an example. We add 37 and 68. Then we say 7 plus 8 equal 15. I write here 5 and carry 1 to the next step. After I compute 1 plus 3 plus 6 is equal to 10. I write here 0 and the carry equal to 1. And finally, I get the result 105. So we can describe the working of the circuit by means of the following algorithm. The initial carry is 0. Then I add the three number x0, the less significant bit of x, y0, the less significant bit of y, and a carry equal to 0. Then, if the result of the sum is greater than 9, I must subtract 10 and put the carry that will be sent to the next step equal to 1. In the contrary case, S0 is the digit, the output digit corresponding to this first step of the computation, and the carry sent to the next step is equal to 0. And the second part of the algorithm is the same, but with the most significant digit of x and y, and using, in this case, the carry that comes from the preceding step. Finally, the third digit of the result is the carry generated during the last step of the algorithm execution. This is an example of functional description by means of an algorithm. The second way a digital system can be specified is by a description of its internal structure, based on the use of previously defined subsystems that we will call components. Let us see an example. We are going to describe a 4-digit adder. For that, we assume that a 1-digit adder has been previously defined. It is a component with 2 decimal inputs, x and y, so that x and y belong to the set 0 to 9, and y binary input carry in, belonging to the set 0, 1. This component computes x mass plus y plus carry in, whose maximum value is 9 plus y plus 1, that is 19, so that the result of this computation is a 2-digit number, and the result will be expressed with 2 output signals, carry out equal to 0 or 1, correspond to the most significant digit of the result, and z, that may be any value between 0 and 9. Then with this component we can define the structure of a 4-digit adder. Actually, the structure of the 4-digit adder corresponds to the pencil and paper addition method. Each 1-digit adder, this one for example, computes the sum of 2 decimal digits plus an incoming carry and expresses the result as an output decimal digit and an outgoing carry, which is transmitted to the next, to the left component. Observe that the maximum value is this one, 19,998. That is to say, a 5-digit number whose most significant digit is equal to 0 or 1. This one is the carry out of the last step of the addition. The previous example uses 4 available components, the 1-digit adders. A 1-digit component, a 1-digit adder, could in turn be defined by its function, for example, by the following piece of program. This is an example of a 2-level hierarchical description. The first level is the structure of the circuit with 4 components, and the second level is the functional description of a 1-digit adder. Let us see an example of 3-level hierarchical description. Consider a system that computes the sum z of 3 4-digit numbers. You can check that the maximum value is this one, so that the result is a 5-digit number whose most significant digit is 0, 1, or 2. The first hierarchical level is a circuit made up of 2 different components, a 4-digit adder, like the one we described before, and a 5-digit adder. Then both the 4-digit adder and the 5-digit adder can be described using 1-digit adders. This is a second hierarchical level. Finally, a 1-digit adder can be defined by its function, for example, the same piece of program as before. And this is a third hierarchical level. To summarize, an hierarchical description is a set of interconnected blocks. Every block in turn can be described by its function or by a set of interconnected blocks, and so on. up to the last level, then the final blocks must correspond to available components defined by their function. Summary of this second lesson: we have given examples of functional description, structural description, and hierarchical description.